So what's the pattern that emerges? What sort of predictions in general were made about insertion mutations? If you're in group I1, I2, or I3, how did that affect protein length? Did you predict? Most of you said it would increase. So in insertion, if you're adding nucleotides, the prediction is it's going to increase the length of the protein. And that was generally the case regardless of whether or not you're talking about inserting 1 or 4 nucleotides, 2 or 5 nucleotides, or 3 or 6 nucleotides. Everybody basically, at the start of class, predicted that that would increase the length of the protein. What about the D1, D2, D3 groups? Your predictions, if you delete nucleotides, was what was the effect on the protein length, according to what's up here. Yeah, the vast majority of you, with rare exception, right? 3 students, deletion. All of you said it would decrease the protein length. If you delete nucleotides from the messenger RNA sequence, it'll make a shorter protein, is what you're telling me. There was a little bit less consistency about how those would affect protein sequence changes, but in general, the vast majority of you predicted, regardless of whether it was an insertion or deletion mutation, predicted that yes, it would change the sequence of the protein. So that's class-wide consensus. The prediction is that regardless of insertion or deletion, number of nucleotides, it should change the protein sequence. But there seems to be a sort of a schism on what happens on the left side of the screen. Do insertion or deletion mutations necessarily increase or decrease the length, the number of amino acids encoded by a protein? We discussed this at the end of class, and some of you did point out that within your groups there was disagreement. Some people said it depends on where the mutation occurs in the messenger RNA, whether or not a mutation would necessarily increase or decrease the length of the protein. So that's the summary from last class. That's where we're at right now. And I'm hoping at least some of you performed the analyses over the weekend to take your mutant messenger RNA and translate it and be able to address these questions. Did the mutation you make actually increase or decrease the length of the protein, and did it change the amino acid sequence? So that's the main goal for class today. Again, working on this concept of understanding and being able to predict how specific mutations would affect a protein sequence. So before we get back into groups, the way this is going to work is very similar to last class. Sorry if everybody sat down and got comfortable. This is the only group work we're going to do today necessarily, so we'll ask you to move once to reform the groups you were in. I just want you again to come to a consensus in your group. Compare your observations. So address these questions. As a group, in general, what was the overall effect? Did your protein sequences increase or decrease in length after you made your mutations? Did they change sequence? And why? So the important part is the why, being able to describe within your group, why did you see that mutations always increased or always decreased protein length? Or why was there a disagreement within your group? Note that the original the original protein sequence was 479 amino acids long. So that was the reference for telling whether or not your protein got longer or shorter once you made your mutations. And as last class, you might have gotten some sort of amino acid sequence. This is not necessarily the start amino acid sequence of NU01. I have not memorized it. But you'll see multiple asterisks potentially when you look at your messenger RNA after you run it through transeq. So you might see something that looks like this. Every time you see an asterisk, that's the position of a stop codon. So you don't know which codon it is. It might be TGA, UGA. It might be TAA, or it might be the other one, TAG, the 3 stop codons. So you don't know what the nucleotide sequence underneath those asterisks is. But what that tells you is that's a position where translation, the first asterisk is where translation is going to stop. So transeq is doing exactly what you told it to. It's starting with the first 3 nucleotides in the sequence, it's using the codon table to translate those codons. And it does that for every codon you give it. That is, when the ribosome is translating, it's going to stop at the first stop codon. The transeq doesn't know you're trying to translate a eukaryotic gene, so it's just going to translate every codon. So it shows you all of these subsequent stop codons that exist in the messenger RNA sequence. So you're only interested in, don't worry too much about it. You're only interested in the number of amino acids up until the first asterisk, because the first stop codon is the one that the ribosome is going to stop translating at. Ribosome doesn't care about what happens after the first stop codon. It's never going to translate those nucleotides in the messenger RNA. Right? In other words, you have a messenger RNA from 5' to 3'. You have a number of stop codons throughout this molecule. But the ribosome is going to start at the 5' end. It's going to read until it encounters the first, well, these T's should be used, mind you. It's a messenger RNA sequence. It's going to read until it hits the start codon, and then it starts translating those into single letter amino acid code. And when that ribosome encounters the first stop codon, that's when it falls off the messenger RNA. So translation stops. That's the end of the amino acid sequence of the protein. So it's the distance between the first start codon and just before the stop codon that's the amino acid length of the protein. It includes the AUG, the start codon, because it encodes an amino acid, methionine. It goes up until the first asterisk or stop codon. So here are the class predictions. So let's start randomly. Let's see, deletions of 2 nucleotides or 5. Group over here. So everybody in the group presumably suggested that their protein length would decrease if you had mutations of 2 deletions from the messenger RNA sequence. Was that true, or did anybody have an increase in protein length?
Yeah, we had one.
You had one decrease in protein length? One increase. And everybody else. So what happened? This is the important part, the why or the how. So can you explain why, when you have a deletion of 2 or 5 nucleotides, you get an increase in protein length? What happened? How many nucleotides did you delete? 2 or 5?
5.
Okay, where was the deletion that you made?
It was in the middle, and I was just trying to find out the kind of got lost.
Okay, that's fine. So you try to find it. So to everybody, how could you delete 5 nucleotides and increase the length of the protein?
Delete stop codons?
So if the deletion included the original stop codon, that would necessarily make the protein sequence longer. But then you said that it was in the middle of the coding sequence somewhere, not at the end. So what can you do to mutate, say, close to the start codon that might still make the protein longer? So deletion of nucleotides makes the amino acid sequence longer. So some of you are saying that you make an insertion of 1 nucleotide or 4, 2 or 5. You see lots of stop codons. Of course, only one of them matters. The first one the ribosome encounters will be the one where it stops, if it's in the reading frame. Why are there so many asterisks? How many stop codons are there? There's 3. How many codons are there? So we have 3 stop codons. We have 64 total codons. So what's the probability, by chance, that any sequential group of 3 nucleotides in a messenger RNA molecule is a stop codon? I don't know. I don't do that math in my head. 21 point. Yeah, it's approximately 1 in 20. 3/60ths. Which means, in general, if you're looking at a random sequence of nucleotides in a messenger RNA, every 20th codon, on average, should be one of the 3 stop codons. How many codons does nu01 have? I don't remember now. How many amino acids did I say nu01 had? Honestly, I don't remember. Somebody help me out. 400 and something? 479. So if it's 479 amino acids, how many codons is that? There's 479 codons. 3 nucleotides per codon is 1,400 and something. Nucleotides. So on average, in a protein as long as nu01, how many stop codons should there be in the messenger RNA sequence? If 1 in every 20 codons is by random chance a stop codon, if you look at 1,400 nucleotides, how many stop codons should there be? The 20th of 1,400, which is what, 70? Which means there's tons of stop codons lurking in this messenger RNA molecule. So if you actually go look at the nu01 messenger RNA sequence, you'll see lots of UAGs, UGAs, and UAAs. They're just waiting there for a frameshift mutation to make them active, to bring them into the reading frame of the ribosome. What this should mean to you is this is how geneticists discover genes. If on average, every 20th set of 3 nucleotides will be one of the stop codons, how do you find where a coding region is? This protein is 479 amino acids long. 1,400 and something nucleotides. How many stop codons exist in the reading frame? 1 at the very end. The last codon is the stop codon. So geneticists look through DNA sequence until they find a long stretch of codons, consecutive triplets of nucleotides, where there's an underrepresentation of stop codons. In this case, for nu01, you would transit 479 codons in a row before you saw a stop codon. And that leaves the geneticist thinking, why isn't it every 20th? Now it's 1 every 479 codons that we see a stop codon. There might be a gene there. So if you look for regions that are devoid of stop codons, that's oftentimes where genes are. Most genes are larger than 20 codons or 20 amino acids long. Most proteins are hundreds of amino acids. They're not as short as you would expect by chance if there was a stop codon every 20 codons. So if you delete multiples of 3, delta, deletion of 3, or deletion of 6 nucleotides, make up another messenger RNA sequence here. We've got a start codon, we've got a reading frame, and we've got a stop codon. Okay, let's see. We're going to play game show genetics. Somebody pick a number between 1 and 12. 2. Okay. Pick a different number. 7? I heard 7. Let's go with 7. Sorry, 2's, I should have specified. 2's in the start codon, so that wouldn't help very much. 7. So we're going to make a deletion of 3 nucleotides starting at nucleotide 7. So if you get rid of that codon, if you delete those 3 nucleotides, what happens to the protein length? It shortens by exactly the 1 codon that we just deleted. What would happen if instead we deleted 6 nucleotides, or 3 nucleotides, let's say, since this is a short amino acid, or short protein? What if we happen to delete those 3 that are in 2 different codons? So it's still shortened. You get AUG, and then what's the next codon? GAG, and then we pick up the original reading frame again. So when you have a deletion, if it's a multiple of 3, it will either delete a single codon, as in the first example, or it will delete parts of 2 adjacent codons. So how much does the amino acid sequence change at most? So we go from a situation where we had 2 amino acids to a situation where now we have 1. So the protein shortens by 1. Is that one new amino acid the same as either of the 2 original amino acids? Is GAG encoding the same amino acid as GAC or CAG? It actually might be in this case. I think GAC and GAG are probably the same amino acid. So that one amino acid that's left could either be the same or it could be different than one of the 2 original amino acids. So there's something special about deletions or insertions of 3, right, the groups in the back, 3 and 6 nucleotides. You make a smaller effect on the sequence of the protein because you don't produce a frame shift. You don't switch the ribosome to reading new sets of 3 nucleotides. You just affect 1 or 2 nucleotides around where the mutation occurs. Is that true? Insertions of 3 or 6, did anybody have? Okay. Somebody delete 2 nucleotides from this messenger RNA sequence to make a longer protein sequence. I'll keep writing some nucleotides up here. So if you're going to translate this in your ribosome, and this is eukaryotic, where are you going to start translating? AUG, okay. So if we're going to do this, we underline each subsequent group of 3. So these are our codons, and there's a stop codon. So this protein, whatever it is, would have 3 amino acids, methionine, and then whatever GAA and GAG encode, and then a stop codon. So somebody delete 2 consecutive nucleotides that makes this protein get longer. And not including somewhere in here. Okay, so delete GA. Which one? The first one of this doesn't matter. Okay. So what happens if we have that 2 nucleotide deletion? Is the stop codon still there? Trick. Ah, right. So I should have been more clear about my question. The UAG is still there, but it's no longer in the ribosome's reading frame, which is what you said. So now, with that 2 nucleotide deletion, what's our new reading frame? AGA, GUA, GGU, UAC, ACC. So translation never stops because we've shifted, by deleting 2 nucleotides, we've shifted the reading frame of the ribosome. Now it no longer encounters UAG as a triplet. It encounters the first UA as part of a new codon, GUA, and then that last G in the stop codon becomes the first nucleotide in a new codon. So that's one way that you can have deletions or insertions that lengthen the length of the protein. If you basically get rid of the reading frame that your original stop codon is in. It's called a frameshift mutation. It shifts the reading frame. What about deletions of 3 nucleotides? Did you get? So what we should do now is have you practice a little bit designing mutations again. So I hope all of you have this set of slides. I provided a short messenger RNA sequence for everybody, and I've repeated it 3 times. You have a few practice tries at this. So we've got the same messenger RNA sequence 3 different times, initially encodes 7 amino acids before you hit the stop codon. So we've got 7 in-frame sense codons, and then we've got a stop codon. So try to design a mutation to this messenger RNA sequence. We'll do this in class. We'll take about 5 or 7 minutes to do this, and then we'll discuss results. Try to design a mutation that fills in one of the blanks, one of the empty spots in the table that we filled in. Length, it's the easy way to increase the length of this protein. Delete the stop codon. So what deletion did you suggest? Anybody who deleted the stop codon, what did you do? Okay, how many, we're doing deletions of 1 or 2, right? Or, well, you could delete 3, but that's easy. So what happens if you just do a deletion of 1 nucleotide? You get rid of that first U. What's the effect on the protein? You get a frame shift. So then you're reading in sets of 3. You've got AAA, GCT, and then what happens? TGA, the stop codon. So a single nucleotide deletion has made this protein that's encoded by this messenger RNA 2 amino acids longer. So deletions can make proteins longer. Insertions can make proteins shorter. There's no way to predict how a particular type of mutation, insertion or deletion, will affect the length of a protein unless you actually do it. Translate it and see, did it change the length or not? What about others of you? Did anybody else come up with other not involving the stop codon insertions or deletions? Make this longer? Presumably there are some. So delete the second to last.
The CGA, just delete that C.
So we could delete, what, like that?
Yeah. It's the same thing as
Yeah, so if we do that on the second copy, then it has exactly the same effect. You get GAU, AAA, CGT, and then you hit the same stop codon. Good. So these are sorts of things that I might ask on exams. Invented mutation that has some sort of an effect on the protein. And all I'm trying to do is reinforce the idea that mutations have lots of different types of effects on proteins, including making them longer, shorter, changing the sequence, and not. Are there any questions about this series of exercises that we've done? You've got the tools to make the mutations, feed them into transeq, find out what the encoded protein is, and compare an original protein sequence to a mutant protein. I'll let you read those at your convenience, not right now, just so everyone's got this on the slide. So the conclusions, which I just stated. The last thing I want to mention is I assigned this assignment weeks ago. Transcription, right when we started the transcription module, the transcription chapter, there's a series of 8 questions down here at the bottom. So I've given you a messenger RNA sequence and the coding and the template DNA sequences. At this point, right, we're done with content for the exam. Review session Wednesday, exam on Friday. At this point, you should be able to answer these questions. Because I have not done my job reminding you that this was something you should continue to work on as we went through the transcription and translation chapters, what I'm going to suggest now is that you work on this and bring questions next class. So this is never going to be due. This is just an exercise for you to practice your understanding. So try to work on this. You should be able to answer all 8 of these questions. Bring questions next class. Wednesday, we're doing a review session. It'll be the same format as always. You ask questions, I give answers, and then we'll do the exam on Friday.
Is that like most of the test?
This is not most of the test right here, but all of these are fair game questions to ask. I would not, and I will not, have one question that relies on correct answers to previous questions. Right? I try to avoid that sort of test structure at all costs. Right? Because if you screw up creating the spliced messenger RNA sequence, you're certainly not going to get the right protein sequence when you translate the messenger RNA. So all of these concepts are critical for understanding the transcription and translation chapters, but not all in one single question. Any questions? Concern? Yeah, please.
Is that Google Classroom assignment that you last noted due for points?
The one that we just discussed.
Yeah.
So the Google Classroom assignment for mutating the NUO1 and assessing the effect is not due. It's just an exercise. I'm just using Google Classroom to distribute it to you. So you don't have to turn it in. All right. Very good. See you on Wednesday.